Yes, sir. Good morning, respected faculty members and my dear friends. It used to be great fun playing with pieces of magnets during childhood. The magical force chasing and pulling pieces used to be thrilling. We never thought the power and possibilities of those forces of attracting and repelling. The same forces of magnetic flux brought great revolution in the transportation system. It added super high speed in land transportation. I, Aryanjali Sharma of 5th semester is here with a short presentation on the same technology popularly known as maglev. Let's have a look at the inventors from different corners of the world. Boris Petrovich Weinberg proposed a vacuum transport project in 1914 that made use of magnetic suspension technologies. Émile Bachelet, the French-born American scientist, explained in detail how to arrange the magnets with the poles in 1914. Hermann Kemper was a German engineer who developed the trans-rapid system and the linear motor car. Dr. Eric Lethway was a renowned British electrical engineer. He is known as the father of maglev transportation. The world's first commercial maglev train became a reality in 1984 when a maglev became operational between Birmingham International Railway Station and the International Airport with a speed of 42 kilometers per hour. Maglev is based on the principles of physics laws, such as Faraday's law of electromagnetic induction, which states that the induced EMF is directly proportional to the rate of change of magnetic flux. Lenge's law of electromagnetic induction, which helps us to understand the direction of the induced EMF or current. With the discovery of superconductivity, maglev trains with superconducting magnets came into existence, which means when the magnet windings are cooled to less than -450 Fahrenheit, they can generate magnetic fields up to 10 times stronger than the ordinary electromagnets. Let's see the two methods of levitating the maglev train. First one being the electromagnetic suspension, also known as the trans-rapid system, and the other one is electrodynamic system. Both of them are shown in this diagram. Let us further briefly understand them in the next slides. Let us understand the electromagnetic suspension from this diagram. This method involves the undercarriage of the train wrapping around the steel guideway. Supporting electromagnets in the train's undercarriage are directed up towards permanent magnets in the guideway. When the support electromagnets are powered, they pull the train up, lifting it about 1 centimeter off the track. The guideway has coils of electrified wire running through it which produce a magnetic field. These magnetic fields change as the current changes in the coils, which pushes and pulls the electromagnets on the train's undercarriage. Let us understand electrodynamic suspension from this diagram. This method makes use of supercooled, superconducting magnets built into the undercarriage of the train. These superconductors are electromagnets which, when cooled to a low temperature, allow for current to flow with very little resistance encountered. This free-flowing current produces very powerful magnetic fields to lift 10 centimeters above the track, push and pull the train. The sides of the guideway contain loops of electrified wire which produce magnetic fields. As the train moves forward, pulled by the electromagnets in the sides of the guideway, the superconducting magnets in the train's undercarriage induce a current in the coils of wire below the train. Let us understand the propulsion system. Both the electromagnetic suspension and electrodynamic suspension make use of similar propulsion system. An alternating electric current is supplied to the coils, which creates a change in polarity of the magnetic field. This pulls the train forward from the front and thrusts the train forward from the back. As an outcome of these technological developments, China unveiled the world's fastest maglev train, which can operate at a top speed of 600 kilometers per hour on 21st July 2021. It's not the end. Further developments are pushing humans to make impossible to reality in days to come. Here is a sketch of future transport system which is presently at experimental stage, and ideal for intercontinent commuters. An exciting future possibility for maglev trains is known as evacuated tube transport. This will make global journey within countable minutes with top speeds as high as 4,000 to 5,000 miles per hour. This involves the train enclosed traveling in an enclosed vacuum tubes with very little air resistance. It is none other than vacuum transport. I conclude my presentation with a hope looking towards future with golden dream come true. Thank you for giving your precious time and kind attention to this short presentation. And here are the references.
Okay, thank you, Aryanjali. Any questions from the students?
I think it's also known as the hyperloop, right?
Yeah, it's also known as the Hyperloop.
Yeah, please direct your questions at Aryanjali, not at me. I'm not the one giving the presentation.
Okay, sir.
Go on, go ahead and ask your questions if you have any clarifications or if you want to know any more detail about any of the topics that you talked about. Feel free to ask questions. One of the parts about the presentation is not only should you be able to present material, but someone should also be able to talk and answer questions about the material they're presented. Satyan sir, do you have any questions for Aryanjali?
Can you remember what is Lenge's law, Aryanjali? What does Lenge's law says?
Yes, sir. It states that it tends to oppose the direction, of the source which produces the magnetic flux.
So where the Lenge's law is applicable here? in your gravitational magnetic levitation? Can you say in
Yes,
details?
sir.
Bolo? Yes,
Yes,
explain it.
sir. Yes, sir. So in this, I guess this electrodynamic suspension. So at the sides, I guess the figure is not that clear. But out here, there are these wires. So out there, the current is they are flowing in opposite direction. So out there, the Lenge's law is applicable.
Not very clear. Anyway, I have no other question. Other teachers may ask questions, students may ask questions.
Prajol sir, any questions?
Yes, sir. So Aryanjali, it was a very nice presentation. Especially, I like the way you had put images and also very, very little text. So that constitutes the main component of making a good presentation, and congratulations for that. So my question is, for this magnetic levitation, what type of magnet do this train use? Is it permanent or how they are like arranged?
So they mostly use electromagnets because this permanent magnets, as we all know, that it's not very strong enough. So they mostly are using electromagnets out here, and they're superconducting magnets as well because it is very strong. Permanent magnets, I mean, it's not possible to create magnetic fields which are that strong to pull and levitate it.
Acha. So, what are the speeds that these commuters can reach? Do you have any idea the speed, maximum speed?
Yes, in the last slide, I guess I've shown it.
Acha.
Uh, this one, this is the world's first fastest maglev train. I guess it's very recent one, and
Hmm.
I guess in the month of July, China had unveiled it. So it's very high. It has a high speed of 600 kilometers per hour. I guess that's the maximum speed it has reached till now.
Acha, acha. So there is this hyperloop also, no? So from this maglev only this
Yes, sir.
hyperloop concept is developed. So what is the difference between this hyperloop and this maglev train?
Out here, they use this vacuum tube thing. They use this vacuum tube, and I guess when I was researching on this topic, they were saying that maybe they'll construct it underwater so that it because on the land surface, I don't think it would be that possible, or I don't think it would be that feasible. So they would be constructing it underwater.
Acha,
And since it is inside a vacuum, so there will be very little air resistance. So that's why it can travel at very high speeds.
acha, very good. Okay, thank you. So I'm done.
Sujata ma'am, any questions?
No, Aryanjali, I don't have any question.
Kharga, Dr. Kharga.
Yes, I have two questions. So, Aryanjali, you were talking about the types of maglev, right?
Yes, sir.
So I couldn't understand. I mean, I couldn't understand the second one.
So this one, electrodynamic.
No, sorry, the first one,
This one,
Electromagnetic.
magnetic. Yeah.
electromagnetic. So
Yes.
out here, there's nothing much out here. This, as we can see out here, this it is wrapped around the this guideway. The trains, this undercarriage is wrapped around this guideway, which we do not find in the electrodynamic suspension. And out there, they are making use of permanent magnets so that it can stay in position. So out here, we can see that it produces a magnetic field out here.
Mhm.
So because of which it kind of is helping it in levitating and in moving forward.
Okay, levitating. We can understand how does it move forward?
How does it move forward? I guess this because of the change in polarity. Out here, it's the propulsion system. So out here, inside the train, I mean, on the sides of the train and on the, I mean, inside the track on which they are running, they are all made up of this magnetic wire. So out here, I mean, constantly being supplied out here. So because of this, there is a change in polarity. So out here, we can see that there is a kind of attraction and repulsion going on, because of which it is kind of moving in the forward direction, and it's kind of propelling forward.
Okay. Okay, that was my first question. And the second one was, you mentioned something about superconducting magnets, right?
Yes, sir.
So do you know, like, how does a superconducting magnet work?
Superconducting magnets. It's produced when we like keep it at a very low temperature, means a temperature which is very very low for like uh, for normal person to even think of, and out there this current is being constantly supplied out there, so they kind of the current is being supplied, and because of this the large current is being able to flow through it, because of which it can easily levitate.
Okay, my next question would be, how does this current flow without much resistance?
Sorry sir, I didn't get your question.
How is this superconductors have low resistance at such low temperature?
That is a question relating to superconductivity, not here in the application part. But my question is, do you think that the train itself and the track over which the train is moving, they are all kept at very low temperature so as to
No
attain
sir,
the,
not.
then how
No sir, it's not
superconducting,
like that.
how
Yes, yes,
superconducting phenomena comes into the picture?
yes, yes.
If the temperature remains at
Because
room temperature, then how superconductivity will come into the picture? That is my question
because
actually.
Hmm.
in the
Yes,
sides of this trains, inside of this trains, there's this magnets. I guess they maintain a very low temperature in this area of
Only the
the
train,
train.
not the track.
Yeah.
Yeah. So the entire train, lengthwise, entire train has got some facility so that the temperature is kept at very low temperature.
yes,
Correct. That is
yes,
possible.
yes, yes,
But
yes.
the cost of transportation will also be very high, I understand. But the time taken to go from one place to another place will be very small, very short as compared to the ordinary movement. 600 kilometer per hour means it is quite high. Anyway, that is a commercial thing. That is a viability thing. Economics part will come. There is no other question. Dr. Kharga,
Yes,
if
sir.
we have
That's
more.
all.
Okay, then, okay.
Thank you,
Proceed with.
Aryanjali.
Okay, Aryanjali, I don't actually have questions for you, but I will give you some feedback. This was a very nice presentation. I quite liked it. I liked your scripting. I liked your delivery. Very clear, very confident. It was really good. And for the most part, for those of you who are watching, this is a good idea of like a good presentation. Now, some of the drawbacks was you are kind of light on the physics. You needed to talk. As you can see, Dasa was asking questions about Lenz's law and things like that. Those are the kind of things you want to insert in. A little bit light on the superconductivity part also. For the record, room temperature superconductivity, as Kharga sir will probably tell you all, is a huge area of research. Lots of money there if you guys want to try going that direction. Yeah, so you're a little light on the physics, and your presentation's a little short as well. I think you were about 10 minutes, and usually we are trying to hit about 15 minutes or so. But aside from that, it's a really nice presentation. One thing though, if you go to your reference slide, can you go to your reference slide? That is not the proper citation. You're supposed to cite it in the APA style. Those are not APA style citations. Please cite them properly, Nick. You need to cite them properly. Now, in this case, obviously, we don't care. It doesn't matter. Like, not like we don't care. Like, when you're presenting to us, it's not something that actually matters to your career. But if you're ever in a conference, or if you're ever in like some sort of like proper presentation scenario, they're going to judge you if they see all of this. You need to present it properly in the APA style. And if you go back to your slide on superconducting magnets, so in general, I really like this. You can see the diagrams really clearly. You can stop there. But for the other ones, you can see the diagrams really clearly. Here, there's a little bit too much text on the screen. So you might want to like change them into bullet points, just so that when somebody sees this for the first time, they see like a big block of text and their eyes will start glazing over. So you kind of want to either break the text up into parts using animations, or you want to put like small bullet points. Okay. But aside from that, I liked your presentation. I definitely like the scripting and the speaking. Very good, very clear. I quite enjoyed it. And honestly, whatever like recommendations I'm giving, they're like really tiny. They're not going to ruin your presentation in any way. I just think that the biggest drawback to your presentation was that it was light on the physics part. All right. But aside from that, it was a really good presentation and I quite enjoyed it. Thank you, Aryanjali.
Thank you, sir.
Does anyone else have feedback to give?
I'm okay, sir. You have mentioned whatever like the thing over there.
It's okay.
Okay. Do any of the students have feedback to give?
Yes, from students.
Now in the Google chat, I have given the link to the feedback form. You're all supposed to be filling it out. If not now immediately, but immediately after this thing is over. You'll get one feedback form for Aryanjali and you'll get one from Priyam as well. So make sure you fill out both the forms. Okay. I don't see anybody else asking questions. So I don't see anybody else asking questions. Aryanjali, yeah, you can stop presenting. Thank you so much. It's a good topic too. I quite liked it.